Let me introduce you. So
Yes.
welcome everybody. Our speaker this week is Bryce. He's going to be speaking to us about differentiation in real topological vector spaces. So Bryce, it's all yours.
Thank you. Appreciate the warm introduction. So yeah, I've got a couple of results on this that I just been working over last semester. I read an interesting piece of Lang's Introduction to Differentiable Manifolds, where he outlines a generalization of the Fréchet derivative past Banach spaces to general topological vector spaces, and then in classic fashion does not touch it for the rest of the book. So I figured it'd be fun to look at. So that's what we're going to be talking about today, the extension of the Fréchet derivative to general topological vector spaces, what goes right and what goes wrong. So before we go and dive into deep water, it always makes sense to stretch our legs in the shallows. So let's look at some familiar territory. So why the hell do we differentiate things in the first place? Well, that's because flat things are fantastic. Vector spaces are really easy to do calculations in, perform operations and solve problems. But there are comparatively few of them when we are looking at all of the possible shapes that we could investigate. There are a lot more curves, and curves tend to be more interesting to far more people. And so wouldn't it be nice if there were situations where we could treat curved things like flat things? And differentiation answers this question with a yes. So there are situations where we can treat curved things like flat things, and I'm not surprising anyone by saying that, because we're all very familiar with this definition of the derivative at this point in our lives. But what this is essentially saying here is that as we get closer and closer to a particular point, in the case of a real valued function of real numbers, we end up getting closer and closer to a particular real number, which we usually denote f prime at x, where x is that point where we're differentiating. And once again, what this is conceptually to mean is that nearby the point x, f looks a whole lot like a line with this slope. It is well approximated by a linear thing. Now, this definition of the derivative is very useful when we're talking about real valued functions on the real numbers, but it's actually not quite as easy to go and take this to other spaces. You can actually generalize this to Banach spaces for the Fréchet derivative pretty easily, but where we're going, we want something slightly different. And that slightly different is going to be just this reformulation. This reformulation here of the derivative. So from the last slide, where we have the limit of the difference quotient, we could actually instead, just by subtracting our derivative onto the other side and doing some very simple manipulations, we could rephrase our derivative definition as saying that near x, we can calculate values of f of x plus h, where h is assumed to be something kind of small, by simply taking f's value at x and then adding that tiny little step that we've taken with the slope that is to be linearly approximating our space, plus some error function, which gets small as h gets small. And it gets small very, very fast in this particular way, according to our definition from the last slide. And just recognizing the parallels with the definition in the last slide, we can actually see that this control function, this error function, its requirement is that it is differentiable at 0 and that its derivative is equal to 0. So it can be linearly approximated by a flat thing right at 0. Okay, so this is the definition of differentiability that we now want to take into higher spaces, because it turns out we can take advantage of the uniform structure of topological vector spaces. All topological vector spaces have natural uniform structure in order to make this definition without having to reference any sort of metrics. So to do that, and then as far as, oh goodness, it keeps double skipping on occasion. There we go. All right. So A couple of these slides are going to be very wordy. They're going to have lots of technical detail for the folks who are interested in reading. But if you're not interested in reading, don't worry. I'm going to give the highlights of what's going on here. So the idea of a little o function is what I was just describing a moment ago. And little o is sort of in reference to the Landau little o getting small notation. So a little o function is well approximated near the origin by something that is essentially the zero function. So the way we end up encoding that is by saying that f is little o if we have what's called a cutoff function, or what I call a cutoff function of f, written f tilde, which is equal to our original function on some neighborhood of the origin, but past that point, it's just zero. And that might seem weird and artificial, but my first example for this definition will explain why that's there. So we have a cutoff function with the property that for any neighborhood of the origin of the codomain, there is a neighborhood of the origin of the domain, and what I call a control function, basically just a real valued function on the real numbers, which has derivative, which is differentiable at 0 and has derivative equal to 0 at 0. So given such a control function, for any neighborhood of the origin of the codomain, there will be a neighborhood of the origin of the domain and such a control function such that this subset relation is obeyed for every single t in the real numbers. And so what this subset relation is essentially supposed to say is that the way that f tilde goes to 0 as we cause our neighborhoods to approach 0 linearly, they approach 0 at a linear scale, is controlled by something that approaches 0 differentiably so that it approaches 0 with a flat tangent line.
So a couple questions.
Yeah, no problem.
One, is this your definition?
Yeah, so this is I've modified Lang's definition. This is equivalent to Lang's definition, but instead of having his control functions defined on the entire real numbers, he only constricts them to neighborhoods of the origin, and that ends up getting rid of the cutoff function aspect of this. That's the only thing that changes. I just prefer it this way for some bookkeeping that happens in proofs, but they're equivalent.
Okay, so a couple questions then. So the neighborhood, I think, W depends on the neighborhood V.
Yes, the W, the neighborhood in the domain.
And the control function changes depending on the neighborhood as well.
Yes, V,
Or
but the cutoff does not. The cutoff is independent of your choice of challenge neighborhood in the codomain.
Okay, thanks.
No problem. That is actually a very good question because that becomes relevant in a whole lot of proofs. So good eye. All right. So first example to see why the hell that cutoff aspect of this is here. And then maybe to give an indication of why Lang's definition doesn't have that problem. Let's take a look at this function, which is defined on the plane in polar coordinates. And it's 0 almost everywhere, but on the unit circle, it is defined to be secant of theta, where theta wouldn't cause it to blow up. And so this function, for any epsilon ball where epsilon is less than 1 around the origin, it's just constant equal to 0. It's definitely well approximated near 0 if this well approximated near 0 business is to be a local property, something that doesn't depend on what's happening elsewhere, just what's happening in an open set at that spot. But without the cutoff part of the definition, this function would not be little o, because let me return back here, as I scaled up any neighborhood for all real numbers, I would eventually get to the point where my neighborhood was larger. It was outside of the open disk of radius 1. And therefore, it would include the points where my function which would cause my function to have an unbounded range. That would be a problem. Oh, excuse me?
Maybe I'm missing something though, because I feel like it should only matter when t is small anyways. So sending t to be...
Yes, no, it should. That once again, you can get rid of this. You can change the whole definition so that it only it only references the small things. It just makes certain things in other proofs kind of harder to look at.
Okay, I guess I'll see.
So, well, I can show you the document with those proofs. I have a couple of things. I have only so much time, so I have a couple of things that I'm proving today, but I don't think it's those that I have where you'll see it. But I can share the document where you can.
Okay,
see
cool. I'd like to see.
Okay. All right. So anyway, so yeah, so with that cutoff now, with that cutoff added, then clearly this function here can be cut off to be 0 everywhere. And then going and finding a control function for any challenge neighborhood in the codomain is very simple. And it's also simple to find the neighborhood that you need in the domain because the whole domain will work. You will end up in a situation, once again, if 0 is a cutoff of your function, then you can just take the whole domain, scale it as much as you want. The answer will always be 0, and that will always be contained in 0 times any neighborhood. So this example also illustrates sort of the trivial case. If something is 0, if it vanishes on a neighborhood of the origin, it's got to be a little o function, which is kind of no duh, but you know, it's one of those good normalization case things that you should check to make sure happens, and clearly it happens here. So now something for something that's a little bit more interesting. So here's an example of a little o function, the functional defined on L2n that just takes any function and sends it to 2n times its norm. This is clearly little o because given any epsilon neighborhood of the codomain, we can simply restrict f's norm to be less than the 2nth root of epsilon. And then when we go and take some inequalities here, what we find out is that the values that f produces, when little f is constrained in such a way, must always be less than epsilon times t to the 2n. T to the 2n is a little o function, or rather it is a control function because it is differentiable at 0. Its derivative is equal to 0 at 0, and it is equal to 0 at 0. So this satisfies the necessary definition. And so it shows that that functional is in fact little o of h, or little o. Okay, so now results for little o functions. Once again, I have the proofs for these written up for the interested viewer. I can share those with you. But for the talk, I'm just going to give a brief outline of why some of these work, unless it's kind of really, really obvious based on a prior result that I've already mentioned. So starting off, if a function is little o, then it is continuous and it also sends 0 to 0. So my brief explanation of that is the existence of any neighborhood in the codomain for any neighborhood any neighborhood in the domain for any neighborhood in the codomain is clearly the thing that's going to give you the continuity that you need. And then you can just use the fact that you have any control function for the codomain being the whole set, and you can find out from that the function has to send 0 to 0 by watching what that subset relation says when t is equal to 0. So this is not very hard to show, and it follows immediately from the definition of little o. A function from the real numbers to the real numbers is little o, if and only if it is a control function, which, if we recall from the definition of little o, meant that it was differentiable at the origin and sent 0 to 0, and was also had a vanishing tangent line, or excuse me, not a vanishing tangent line, had a vanishing slope at 0. So in other words, this little o definition that we've introduced, it's eventually going to be the same as being differentiable at the origin and having 0 as your derivative at the origin. And I have to define differentiable first before I can prove that. But right now, I'm assuming that we already, going into this, I have to assume that we know what it means to differentiate real valued functions. But all the other ones can follow from the definitions. So it makes sense to show that the definition of differentiation that we already have, the one that applies to real value functions, it coincides with the one that we've just come up with. So, and it does. And it's this one is actually a little bit of this one is a little bit of a challenge, but it follows from the fact that you can divide real numbers by other real numbers. The real numbers are a field, and so a whole lot of these inequalities that you end up writing down from the subset relation in the definition of little o can be reversed or coordinate swapped to give you the correct relationships that you need. Okay, so the third result that I'm going to need is this one that is related to something that's called the Gateau derivative. I haven't mentioned the Gateau derivative by name anywhere in here, but briefly, it is the generalization of directional derivatives to any vector space. It's also metric independent, though most of the time people are happy to work with Gateau derivatives only in locally convex topological vector spaces. They actually can be defined in arbitrary ones. And here, what this is essentially saying is that a Gateau derivative, because we don't have uniqueness of derivatives here, no Hausdorffness is assumed for our vector spaces, so things aren't necessarily unique. But a derivative of a little o function at the origin, or excuse me, a Gateau derivative of the little o function at the origin is 0 for every single direction. So directional derivatives of little o functions are 0, which is a prelude to the fact that if the definition of the derivative, or excuse me, if something is differentiable by the definition we're going to show here in a second, then it will also be Gateau differentiable, and all of its Gateau derivatives will line up with its Fréchet derivatives.
That is, if the two derivatives make sense.
Yes, exactly. If the two derivatives make sense. If we have something that's Gateau differentiable but not Fréchet differentiable, then that's not going to work out. You can be Gateau differentiable, directionally differentiable in all directions without being Fréchet differentiable. And the classic example of this is actually the function in the plane x cubed over x squared plus y squared. That function, you can investigate it to your heart's content. Its homogeneity will guarantee that you can take its directional derivatives all you want. But if you were to do that, you would find that its directional derivatives depend non-linearly on the direction that you take its derivative in. And so it can't have a Fréchet derivative because such a Fréchet derivative would then have to be a nonlinear function of its argument. And as you will see in the definition, they are going to need to be linear, so that would be a contradiction. Okay. So last two results here, and these I'll be even briefer about. So the 0 mapping is always going to be little o, but if the codomain of the spaces that we're talking about it is actually Hausdorff, then it is in fact the only linear map which is little o. So the only linear thing which is little o, that is, which is flat at the origin, is the 0 map. And once again, this is another sanity check normalization case. Good God, that better be that way, otherwise something's wrong. And it does work out that way in Hausdorff spaces. So this is the clue that a whole lot of uniqueness and other things that you're going to want that is usually guaranteed by Hausdorffness as far as limits is concerned is also going to extend to differentiation. Okay, and then the last thing to mention here before I get on to the next definition, the collection of all little o functions from any real topological vector space to another one, that will always form a real vector space, not necessarily a real topological vector space. You can't necessarily put a topology on, but it will be a vector space. It will admit an addition and a real scalar multiplication. Okay. All right. So that concludes all of the basic results that I needed about little o functions to make sense of some of the other things that are going to show up. Now I can finally talk to you about what it means to be differentiable. And if you thought that the little o definition looked weird and had some artificial strange parts of it, this also does, but I can explain them as well. All right. So given a point in a real topological vector space and a function from a neighborhood of that point to some other subset of another real topological vector space, we say that that function is differentiable at x when there exists an extension f hat here of I circ f, where I is the canonical inclusion of that subset that I mentioned earlier, V, into its parent real topological vector space, So I sort of need to by extend my function in order to ask whether or not it's differentiable. I need to extend it in the usual sense to x in its domain instead of just u. And I need to co-extend it in the codomain to the whole y instead of v. And the reason I need to do that is because I eventually need to do some algebraic operations on it and then ask if the resulting function is little o. And little o is only defined for functions between vector spaces. It's not defined between arbitrary subsets or neighborhoods and so on.
So I don't understand why you didn't define f on the whole space to start with.
Because now this will apply to this applies to arbitrary functions defined on it can be applied to functions that are defined on the whole space, but now it will also apply to functions that only are defined on neighborhoods. So this is just more general.
Okay.
It's like, yeah, a little uglier, but it saves me having to have, all right, here's the definition of differentiability if your domain is all of x. Here's the definition of differentiability if your domain is
no, but to me it seems, I mean, especially if you're working in this generality, to me it tells you that you're working with a topological vector space, which is not going to be, well, Banach, essentially. It doesn't have norm, or its topology isn't generated by norm. And typically in that situation, I mean, at least in practice, any example I can think of, any functionally defined or any function between two such vector spaces is defined on the whole space to start with.
Okay, so but that doesn't eliminate the possibility of potentially studying other situations like, for example, spaces that are locally modeled on topological vector spaces, in which case I would need something like this. Because then I don't necessarily know that the entire space that I'm talking about.
Okay, sure, but can you give me an example of such a space? Or
No, but that's the whole point is this is a set of notes so that I can work on things in that level of generality. Yeah, I don't have example of that yet, but I want to be able to talk about them if I start looking at something like that and I see it that way.
Sure, okay. I'll have some more questions in a second, but.
Sure thing. Okay, so anyway, yeah, so we've by extended our function up to so that its codomain includes, or so that its domain includes the entire domain topological vector space, and likewise for its codomain. And then the question that we ask about this by extension to see if f is differentiable at x is whether or not there is a continuous linear map such that this expression right here that we write down, the difference between our function at a spot plus something presumably small, but it doesn't necessarily have to be, minus its linear approximate is a little o function. So if this is the case, we say that f is differentiable. And if it's true for some subset of the domain, that subset which is included in the interior of our domain, crucially, this definition only applies to points which are in the interior of our domain. Then we say that f is differentiable on that set. And if f is differentiable on its whole domain, then we just simply say it's differentiable, like usual. So there we go. So long-winded, I know, but that is the definition for differentiability here. And yeah, no, these, as far as it being ugly and not necessarily being as short as desired, I'm right there with you. This is absolutely still a work in progress. One of the things that I think I mentioned at the beginning of the talk is I don't actually have a reference for these things. This is what I worked out last semester because I was curious about all this stuff. And Lang basically mentions that all of the things are true, but he doesn't give any references. And in my reference search, I wasn't able to find them. So this is my patchwork set of tools that I made at home so that I can figure out what the hell that Frenchman was saying.
So perhaps there's a reason why. But I mean, the important line I think is the third from the bottom. Yeah, it's just that what is derivative? You move by a little bit, and whatever you have linearizes.
Yeah, exactly. Yeah.
Plus something.
And this will be the same regardless of the minutia of how things are defined and whether or not you need cutoffs or extensions or any of that stuff. This will always be the case. You're going to be trying to define what it means to be a little o function, however you go off defining that.
Right, but then that seems like, okay, so this is back to the original point. I mean, I think Lang's definition has the little o function defined even on subspaces, yeah? Or it would be perfectly well defined on subspaces. So then you would need this extension result, yeah?
I was under the impression that it was defined in the entirety of spaces, but it might just have
Point is that it
been,
localizes in the space near the point that you're at, so it doesn't matter what happens outside.
perhaps it might have been, I was working under the assumption this whole time that it was specific to, actually, no, wait a minute. It wasn't even that. It was literally just for bookkeeping various epsilon neighborhoods. Like I've explained to you, like I mentioned, there are a couple of proofs where I didn't like what happened with Lang's definition on having it localized to neighborhoods. And it was essentially just a matter of bookkeeping epsilons. If
Sure,
you're,
so maybe it's the definition is more complicated here, but then the proofs are easier, something like
Yeah,
that.
yeah.
I can buy it. Okay.
So, and, there's definitely something to be said for having simple definitions, but clearly that's clearly not the route that I took for this. This is also definitely not the final version of this talk that I would give. I started working on it at the beginning of this week when you asked if someone was going to give a talk this week. And I was like, you know what? See if I can pull something out. So, all right. So now important results concerning general differentiation. So we have this definition of the derivative. The questions we'd be interested in asking is, all right, what works and what doesn't work? First of all, another sanity check, as always, constantly giving yourself sanity checks is a good way to stay sane. Any function which is defined between open sets of the real numbers is differentiable at a point, if and only if it's differentiable in the usual sense. That follows from that earlier proposition on little o functions, that they were little o if and only if they were differentiable at the origin and vanished there with their derivative. So this follows very quickly from that. Likewise, functions are continuous where they are differentiable, at the points where they're differentiable. This ends up following from the fact that little o functions are continuous at the origin. You can use the linear approximation relationship to rewrite a function as a sum of a constant, a continuous linear function, and a linear o function, or excuse me, a little o function. And all of these things will be appropriate at they will be continuous at the appropriate point to make our resulting function continuous there. All right, and then next, another sanity check. A linear transformation between topological vector spaces is differentiable if and only if it is continuous. So what it means to be a differentiable linear transformation is the same as what it means to be a continuous linear transformation. And likewise, and moreover, rather, this linear function is approximated by itself at every single point. So this one is slightly long again, but this is the follow-up to the Gateau derivative result that I brought up for little o functions. And here the extension bit really doesn't matter at all, because once you're taking this limit, it's only occurring to t getting small, but I seem to have not done that when I typed this out. But regardless, what this proposition is saying is that if a function is Fréchet differentiable, or differentiable in the definition that I provided earlier, then any of its directional derivative and any of its Gateau derivatives will also be defined, and they will be equal to the associated Fréchet derivative in that direction. So this is, and this is also that relationship between the Fréchet derivative and the Gateau derivative is well known and generally studied in Banach spaces, because the Fréchet derivative is not usually studied in locally convex spaces, but most people only talk about Gateau derivatives there. But they can both live there happily, and they still have the exact same relationship that they had in Banach spaces. Okay. Onward. We're almost, thankfully, I'm making good enough time. I think I should be able to make it to the main result. So things are looking good. All right. So a function is little o, a function between topological vector spaces, is little o, if and only if it is differentiable at the origin, sends the origin to the origin, and is well approximated by the zero function at the origin. So what we would expect a little o function to do, it does. The vector addition, the vector addition and scalar multiplication of any real topological vector space is necessarily going to be a differentiable operation, or necessarily going to be differentiable operations under this definition. So that's good. That all of that still makes sense. At some point, something's going to stop making sense here because too many things have been nice, but we haven't made it there yet, but it's coming. All right. Next up, just like the set of all little o functions between any pair of topological vector spaces turned out to be another real topological vector space, if we have a neighborhood of a point and the collection of all functions which are differentiable there and mapped to some other real topological vector space, then this set will also be a real topological vector space, and it'll do so for the exact same, for essentially piggybacking off of the fact that little o functions were. So yeah, we end up with vector spaces of differentiable functions, just like we expect. And the derivative map, when our codomain is Hausdorff and the derivative map makes sense to define because it will be uniquely valued, it ends up being linear on this vector space as we want it to be. Okay. Oh, you already saw that pathology is coming, but here's the last two. Here's the last two results. Before
Okay, back to the slide. It's still going to be linear, even if it's not Hausdorff. It's just the map isn't going to be uniquely defined.
No, yeah, it'll be a multilinear potentially now.
Well, it'll be linear. It'll just be multi-valued. But yeah.
Well, but like if it's multi-valued, then it's not a function.
So pick a particular value of each, and then it's linear map still. It may not be differentiable or smooth or whatever you like it to be, but it's still going to be linear.
Oop, come on, you. Give me a second. Oh, there we go. All right. So now some pathology. So I shared a bunch of nice things that this derivative does. It has a whole lot of the properties that we would expect derivatives to have from having worked with derivatives all our lives in elementary calculus. But it's not well behaved. It has some oddities about it. And this isn't the only one. This is just the only one that I really have a good example for at the moment. So if your derivative is equal to 0 everywhere, even in Banach spaces, that means you're locally constant. However, this is no longer the case in general real topological vector spaces. Being locally constant is no longer equivalent to having a vanishing derivative everywhere, as illustrated by the following example. So we can consider the curve from the positive reals into the not locally convex space, the locally concave space, L1/2. And so where we're going to define our curve to be equal to the, at every single time t, the characteristic function for the interval from 0 to t. And in particular, if we take the norm of the difference quotient and send it and take the limit, as we would in order to take the derivative, because this is now just a function defined on the real numbers. So taking a derivative looks exactly like taking a derivative used to look. And you know, we've even got a norm here to make sense of how to take this limit. And if we go through the calculation, what we end up finding here, because characteristic function, any power of it that's non-zero is, or any positive power of it is going to just return that characteristic function right back. And delta is going to pop right on out of here. We're going to wind up, after squaring this integral over a length, over an interval of length delta, with the limit of delta as delta goes to 0, which is 0. So this is the derivative of our curve at every single point in its domain, 0 everywhere. But this curve is very clearly not constant. As an example, take t is equal to 1 and t is equal to 2. The difference between these two functions will be another characteristic function, the characteristic function of the interval the interval from 1 to 2. And this guy is not equivalent to 0, even in L1/2. So what we've got here is a non-constant function with a derivative equal to 0 everywhere in its domain. So spooky, spooky things happening afoot. All right, so that's some scary awfulness, but not all things here are scary and awful, as the other results that we were looking at saw. Something kind of lovely ends up happening here, actually. The chain rule still works. So composing functions which are differentiable results in differentiable functions, which is, once again, that's kind of a miracle with all the things that could have gone wrong. How lovely. So in order to see this, I've just got a couple of, and by couple of, I mean 5, results that are sort of like lemata that I use to end up proving the chain rule. And these are going to be concerning what happens when you compose little o functions with differentiable functions or linear functions. Sort of like special cases of the chain rule where one of your functions has a vanishing derivative or is linear. And what we end up finding from these special cases, the composition of 2 little o functions has got to be little o itself. This is like taking 2 functions which have vanishing derivative at the origin and both map to the origin. If I take the chain rule with them, I'm just taking 0 times 0. So it's still going to be 0 afterwards. On the other hand, if I start with a little o function and then compose that on the right of a continuous linear function, once again, we could think about this in terms of spaces that we're used to using the chain rule. And this would just look like taking the derivative of a linear function, which means doing nothing to it, and then multiplying it by the derivative of the inside function, f, which we know is going to be 0 at the point in question. So this sort of combination should also give us a little o function, and lo, it does. It does, in fact. So we can compose with continuous linear functions on the left of little o functions to get little o functions. And then finally, the sort of step up from this thing, if something is well approximated by a continuous linear function, then maybe it too has this property. And yes, in fact, if you've got a function which is little o, a function which is differentiable at the origin, maps the origin to the origin. It doesn't have to vanish at the origin, though. It can have any linear approximation at the origin. Then again, we will have that the composition is little o, and the chain rule argument still works exactly the same here. The other 2 propositions are literally the last 2 propositions, but with the order of composition reversed. So essentially very little has changed, but the reasoning is the reasoning is the same as a result. And all of these together, these 5 results on knowledge of when composing with a little o function will give you another little o function, is sufficient to make the proof of the chain rule short enough to fit on 3 slides. So, and short enough so that I can actually get to it. Thank goodness. We'll actually have just barely enough time for people to ask questions. Okay, so the chain rule. If we've got a function differentiable at a point in the interior of its domain, and another function which is differentiable at the image of that point, which is also in the interior of its domain, then their composition is going to be differentiable at the first point. And one of the derivatives of this composition at the point in question is going to be the composition of the 2 associated derivatives from our input functions g and f. Once again, no uniqueness. So any choice of such derivative functions we could compose together to get a derivative of the composition. And if they are Hausdorff, then in particular, we have this relationship that everybody recognizes from differential geometry, hopefully. Okay. So now to actually go through the proof, F's differentiability gives us this relationship here for an extension of F and a continuous linear map. Similarly, G's differentiability gives us this relationship here for another continuous linear map and G's own extension. So now what we can do is we can insert this fellow up top into G hat and start using the fact that we know how G hat treats sums like this. So onto the next slide. So I've inserted F hat at x plus u into G hat, and then used our knowledge of what F hat at x plus u can be represented as by its differentiability, its linear approximation plus some small error function. Now we know how G hat treats sums. By its differentiability, this is going to be G hat compose F hat at X, which is just G hat of this first term. And then we're going to have to start sticking into our linear approximation for G, these second terms that appear in the argument. And the same will be true for the little o error function in our definition or in our use of G's differentiability. Okay, so now this last expression right here, we can use the fact that LG is linear to break up its evaluation on these two terms. And what we'll find is the composition of two continuous linear maps with each other. That will give us a continuous linear map. And the composition of a continuous linear map with a little o function, which we know must be little o. So we have a little o function here. On the other hand, right over here, we have a little o function composed with, this is a differentiable function which vanishes at 0 and is well approximated by LF, because this is what it means to be such a function. You are equal to your value, which is 0 here because it doesn't appear, your linear approximate plus some error term. So we know from our previous set of results that a little o function composed with a differentiable function mapping 0 to 0 has to be little o. So this term over here is also little o. The fact that little o functions form a real vector space means that we can simplify our results to this final relationship, which is clearly what we need to see that G hat composed with F hat is differentiable, and also that LG composed FG is a derivative. So the last thing to mention here, a little bit of bookkeeping on the extension stuff, because I mentioned that these extensions, this fellow has to be an extension of the composition, but it is in fact because of the way that inclusions work with restrictions. So that follows very, very, very easily from the concept of subset restriction of maps.
So isn't this just the proof of the chain rule with different notation, essentially?
Yeah, no, essentially just no metric. No metric, no norm.
Yeah.
And that's, I mean, you know, there's nothing inspired on my part coming up with this. I literally just took what's in your favorite calculus book and they're just like, all right, what can I do by replacing things with neighborhoods? You know, it is literally exactly the chain rule for other spaces. It's just, yeah, this one doesn't necessarily require talking about a norm in order to define.
Sure.
And that's my conclusion. I have a single reference, which was the starting point of it all, Lang's differentiable manifolds, and that is all. So thanks, folks.
Yeah, thanks for talking. So let's thank our speaker really quick. And did anyone have any questions? I know I have a few. So.
So,
oh, Logan has a question. Okay, Logan.
when you wrote for the chain rule that that thing was one of the function's derivatives, right?
Yes, one of the possible derivatives. You'll find all the possible derivatives of the composition by finding all the possible derivatives of the two functions you were composing, and then composing them together in all combinations.
Right, but could you like give an example of that? Because I'm struggling to find out how you would get multiple derivatives for a single function in this case.
I'm going to have to go look at some non-Hausdorff real topological vector spaces to do that, but that's not something that I came up with an example of today. But I will absolutely do that. I have interest in making this topic a little bit more accessible, because I wasn't able to find in my perusal of Google and so on a whole lot of stuff talking about this particular topic, which is a shame, because I know for a fact that somebody has done this before, because Lang literally at the beginning of his book mentioned that it was all already known, but I just can't, you know. So the answer is I don't have a great example, but I'm now that you've seeded the idea in my head, I will look into it, and if I can come up with one, I'll definitely share it with you.
All right. And another thing is, if we know the chain rule holds, do we know like any other things hold for the normal derivative, or just that so far?
So this is as far as so I have a conjecture that I've been working on, but I don't have it completely worked out yet. I have most of the results dealt with, but it's essentially there's sort of a, I suppose it depends on how you look at it. There's a modification of the inverse function theorem. So the inverse function theorem applies when you have an open set on which your function is continuously differentiable and a couple other things. It's got a derivative, which is also continuous and invertible and continuously invertible. But it turns out on Banach spaces, you can sort of come up with a pointwise version of the inverse function theorem, where you require that your function is just differentiable at a point and strongly open there, such that its derivative is continuous and continuously invertible there. And then that is actually sufficient to guarantee the inverse function, if it exists, is differentiable there. And in particular, that implies that if a homeomorphism is differentiable, then it is necessarily a diffeomorphism. But I am still in the, I have one little bit of that is still causing me some trouble. So I don't have it fully worked out yet.
Here's a comment that you may not like. When you were talking about the proof of the chain rule, you took from a calculus book and you essentially removed all the metric stuff from it. So now it's consisting entirely of a discussion of neighborhoods.
Mm-hmm.
So the question then becomes exactly what hypotheses do you need to prove the chain rule?
Yeah, no, absolutely. This sort of now it opens up a whole new discussion of, well, what exactly is, what do you need to talk about differential structure really?
Okay, so that kind of question is actually the kind of thing that is addressed by a collection of people in category theory, whose primary purpose in life is to find things that are already known in some branch of mathematics and try to figure out exactly how far they can generalize it. So you essentially try to reduce the hypotheses to algebraic statements in the language of category theory, and then see exactly what hypotheses you need in order to make the proof work.
Mm-hmm.
So that may actually be the place to look if you are looking for where people have pushed these things. The reality is that there are lots of holes in the mathematical literature, so there may not be anything there. I'm working in an area involving category theory where it appears that there were a bunch of people who were working on the area in the late 20th century, but then they all died of old age. And so now it's being picked up by a bunch of people who don't know anything about category theory. So it may be that there is something there in the literature or there is not, but that may be one place to look.
Okay. Thank you for that suggestion. Any other questions?
Is it my turn?
Yeah, tear me up.
All right, so the first is, here's a bold claim. If you have algebra structure on this vector space, so you can multiply vectors and the multiplication is differential with respect to the definition you gave, then things like product will hold and quotient rule.
I haven't checked that, but that's a great, that's an excellent next step to take, because that would be highly desirable.
So it only certainly require that whatever differential or multiplication you define is differential. And that sort of leads into my next question, which is, I mean, to be blunt, who cares, I guess, kind of.
Mm-hmm.
It's a kind of a bad question. You never ask someone who cares because it's interesting to you, so that means it's interesting. But really the question is, I mean, I've done analysis for a while. I can't say I'm an analyst, but I can only think of really one example of an interesting space and application, which isn't, we'll say, Banach. Maybe two, if you look harder. So what's the motivation, I guess?
Are you familiar with diffeological spaces, differentiable spaces, and Froelicher spaces?
No.
So there are various generalizations of the concept of differential structure. So manifold is obviously the most notable definition of differentiable structure, but there's lots of other ways that you could define a differentiable structure on a space, and diffeologies, differentiable structures, and Froelicher structures are another answer to this question. However, no matter which one you pick, you end up losing some amount of information that you had when you were in the case of smooth manifolds. Some amount of the differential structure is lost. My interest in this particular topic was in kind of understanding better what exactly is the difference between the abstract differential structure of finite vector spaces and infinite vector spaces, because that has a lot to do with this sort of loss of information that's taking place in these different structures. This is because the reason those structures were invented was to give infinite dimensional spaces flavor. You can talk about infinite dimensional manifolds, and people have. There's a great book, Global Analysis, I believe, by Mykor and Kriegel, where a whole lot of this is discussed. But the long and short of it is infinite dimensional manifolds in the traditional sense end up being kind of awful to work with in a lot of ways. But these new structures, even though they lose information, they end up sort of being nice and doing lots of fantastic things. An example of this would be investigations of what's called the irrational torus. So that's probably diffeology's main claim to fame, is there's this thing called the irrational torus. If you try to study it with other methods from differential geometry, you get nowhere, but diffeologies are the answer. So that's my whole interest in this, is I want to better understand differential structure in these spaces so that I can better understand the relationship between these different types of abstract differential structure.
Okay, but back to the example you just mentioned, which is, what did you call it? This torus?
The irrational torus. Yeah, what I've been talking about has almost nothing to do with the irrational torus, but that's just like why diffeology is well known.
Okay, we'll have to talk in a little bit.
I'm happy to talk about all of this stuff because I haven't found I'm surprised by how few people know about actually all this stuff, because like John Bayes and a whole lot of other people have been like harping on diffeology and diffeological spaces for a while, but
I still don't see exactly, and maybe you can explain later why it's interesting, because if you get rid of the differential structure, then it seems like for a lot of people, you kind of, myself included, I guess, you kind of lose interest, because the differential structure is what gives you nice things to start with. But maybe there's reason.
Sometimes it's too rigid, right? So maybe there's a way to loosen the rigidity on it to make it still useful for the reasons that you thought it was useful, but more widely applicable. That's the whole philosophy behind those.
Maybe I think the only complaint I have with this talk is there weren't enough examples. There need to be like
yeah, sorry. My modifications of this talk in the future will provide far more, especially counter examples of
examples which don't have norm. That's sort of to me, that seems like the whole motivation here. You start from the beginning with, I think the only thing really novel here was that you have, well, vector space which doesn't have norm naturally inherited, and you can still talk about differentiability just by this notion of closeness and linearization. The rest is essentially the same. You have to replace the word. Well,
yeah, exactly. It's standard differentiation theory, but just now in reference to this new definition of derivative. Yeah.
So it'd be nice to see some examples of like how this works, I guess, in cases or spaces which don't have this structure, I guess, or they're already like a nice norm, not Banach spaces.
Sure. If people are interested enough and this eventually ends up, if I end up making a sequel to it, then that's definitely something that will feature more as both obviously answer to some of the questions that have been asked today, but also examples of things that
I'm definitely interested. It's just, I'm definitely interested. Just like I like to see examples. So, but yeah, okay. So, cool. I think that's all the questions I have for right now. So
Wow, I managed to
Question-
do that in perfect time. Look at that, 12 o'clock. Or
12
3
o'clock?
o'clock.
3 o'clock. Excellent. So questions from anyone else? If not, let's thank our speaker one more time. Thanks again for talking and on such short notice. There's technically no speaker for next week, so if you want to continue your talk, or if anyone else wants to give a talk, let me know.
No, I'm not ready. I was hardly ready for this one, so I'm not ready for the next one. Thank you all for dealing with me for an hour. I appreciate you guys showing up.
We stop the recording.